You go with AC Unit 1. So I titled this one The Context and History of Automotive HVAC, mainly because this isn't going to be all about AC, how to fix AC, how to diagnose. We're not even going to get into pressures. We're not going to get into much about AC other than giving you an overview of why we do AC repairs the way we do and kind of like the history. All right, so first, it's going to be super basic. When we get into diagnosing the vehicle, we need to know about the service history. The reason this is important, some jobs that we have to do will require us to recover the refrigerant out of the system. So let's just say a car comes in and their concern is the AC blows warm, which is the most common concern in AC. If you were to see that they were to recently have had the engine replaced. You know, when you go to replace an engine, you have to pull the AC compressor off. Typically, to pull the AC compressor off, you have to recover the system. After you're done putting the engine in, you're supposed to recharge the system, do the full AC service. But in the case that they forgot, it would come in for AC blows warm. Maybe they had the engine done in the winter, and by the time it's summer, they just realized the AC doesn't work. Um, or if the AC doesn't work and you notice they did a job recently that might have to do with disconnecting AC lines, you may first want to go right to where those disconnections were and see, if the leak happens to be there, right? So if a car comes in, knowing the history can help us kind of pinpoint maybe where to start our diagnosis. Make sense? So consider that. Um, of course, another thing is technical service bulletins. AC's one of the first classes we typically cover that's more diagnosis in its focus. So you really need to get in the habit of checking for TSBs. TSBs may or may not be the issue, but to make it really clear, if you let's say you spend an hour diagnosing an AC concern and then you realize that there's a TSB on it, you may or may not get paid that hour. Like if it goes warranty, you're not going to get paid that hour. If it's already warranty when it comes in the door, you're not really supposed to do a bunch of diagnosis testing. You're supposed to check for TSBs first. So if you check the TSB and you find, oh, AC blows warm, check for this, and this because it's a common failure. It's a repeat failure. There's a pattern. It's a pattern failure. They know that this is failing. You need to check TSBs first, see if they apply and if they match the symptom. Cool. So just both of those things are worth mentioning. Another thing that you all need to be familiar with is under the hood, there's this refrigerant sticker. All right. So we're going to break down some of the points right here. So if you look at this, it's showing you what type of refrigerant it is. You see that R1234yf. That's the latest refrigerant currently used. It's also telling you right below that the capacity is 5.2 fluid ounces of oil. Now I want to pause right there because people get very confused. That's not how much oil you put in. That's how much oil the whole entire system should have in it. So if you take, let's say, a condenser out and you put a new condenser in, you don't put a whole nother 5.2 ounces of oil in. But if you were to have the vehicle and replace every AC part, or probably more realistically on the assembly line, right? They put in the compressor and the condenser and the evaporator and all the lines. On that initial charge, they will add 5.2 ounces. Kind of makes sense. So how much oil do you add after your service? Anybody think they know? 5.2? Anybody for a 5.2? And the correct answer would be it depends on how much came out. So I can't actually answer that. But if a car's, working and you have to recover the refrigerant to do an engine or something, you'd recover the refrigerant and some amount of oil is going to come out. And so you need to make a little mark on the used oil recovery tank and then see how much oil is in there after you do the recovery. And that amount right there, that's how much oil you put back in. Cool. However much comes out, you put back in. It's not like an engine where it burns oil and the oil's burned up and it goes out the tailpipe and you have to keep, topping it off. the AC system is sealed. 5.2 ounces of oil in this case. That's it. It only takes 5.2. You don't have to add to it ever. Well, unless there's a leak. And if there's a leak, how much oil went out? I don't know. And how much oil should you put in? I don't know. It's kind of a guess. All right. So I really like to explain this extensively because this sticker will show you how much oil it should have total, but there's no dipstick. There's no real way to know how much is in there. All right. So deep, deep, deep in the service manual, it'll actually explain to you what you should do. If it has a leak and you don't know how much oil's in there, technically what you're supposed to do is recover the system, drain all the oil out of the entire AC system. Like, so for example, there's going to be a little bit of oil in your evaporator. How would you get the oil out of the evaporator? Well, it's behind the dash. Actually, you really, by the book, you're supposed to remove all the parts and drain them into an oil drain pan, and then get all that oil and put it into like a test tube, like a laboratory beaker, if you will, and measure how much oil was in there. And then you're supposed to if you drained all the parts, then you'd put your 5.2 fluid ounces back in. But if you, for example, took out, let's say, that evaporator and you drained it, you should be able to measure how much oil came out with that evaporator that you just changed and put that amount of oil in addition to the amount that was recovered by the machine. So I guess the short version is it's hard to say exactly how much oil. All right. So when we do this service, when we do these jobs, you just have to be aware if some oil comes out, you want to put that much back in. If it's been leaking and you can tell there's green dye and the green dye is carried in the oil, that means it lost some oil. Sometimes when we do the charge, we might put a little bit more back in than came out just to sort of guesstimate how much it might have lost, but it's not really an exact science. The only way would be to drain the whole entire system, which literally involves taking parts out, turn them upside down, and measuring the amount of oil. All right, that's the matter of fact. Now I'll give you kind of like the flat rate version, because remember, the service manual is typically written by engineers, and engineers are smart, but they tend to not live within the realm of time. So they'll say, oh, well, the way that you know how much AC is in there is you have to drain the whole entire system and drain all the parts out in the oil drain bucket and measure it. And you're like, the customer just came in like for a basic AC line replacement. I can't charge them 30 hours to pull every AC part out of the car and drain it. Like, I can't make the car that big of a project. So the flat rate tech, most likely, what my mentor taught me was every car that comes in, every service we do, he would put in like 2 ounces of oil. And looking back on it, that was probably excessive. So here's the negative of that. If you over oil it, that oil takes up space in the AC system and it doesn't change states the way refrigerant does. And if you have more oil, it affects the way the refrigerant change of state occurs. It won't get maximum cooling. So you could actually have excessive refrigerant oil in the system, and that'll reduce your cooling ability. So your AC might blow warmer. You'd have to have a ton of oil to have it actually blow ambient temperature, I'll admit. So putting too much oil is not good. Now there's an alternative. What do you think happens if you put no oil? If, let's say, the system leaked and it leaked out pretty much all the oil, you go to do the AC service, you don't inject oil. What do you think is going to happen there? Any ideas? Well, the main thing that comes to mind for me is the compressor has parts. Like, there's different types of compressors, but if it's an axial piston type, there's actual pistons going back and forth. How well you think that's going to work with no oil, right? You're probably going to end up seizing that compressor, blowing that compressor up. So know the fact of the matter. It's a little difficult to know how much oil to put in. If you under oil it or you have very little to no oil, you could damage the compressor. Don't ask me how I know, I will tell you, but not today. Or if you over oil it, you can slowly reduce the performance of the AC system. So it's not an exact science, right? I'm just letting you know. The only way to know for sure is to measure the amount of oil that comes out. Makes sense? And when there's a leak, you don't really know how much oil came out because it leaked on the ground. All right. So as we get into the service a little bit more, you can by all means reference this sticker, but that amount of oil is not how much we put back in every time. Are we clear? All right. Now coming on from there. This sticker is interesting. It's a Ford sticker, but if you notice right here, it talks about on the 1.5 liter or the 2.7, on the 2 liter, on the hybrid electric vehicle. So it depends on what engine's in there. They all run R1234yf Option refrigerant, but they have varying amounts of refrigerant. So the 1.5 or the 2.7 call for 510 kilograms of refrigerant. That's not oil. That's the refrigerant, 5.510 kilograms of the R1234yf. Make sense? But if it's got the 2 liter or the 2.5, it actually takes a little bit more, 0.624 kilograms. Now, if we were to make that into a little bit more of a familiar unit for the US scale, that's 18 ounces. 510 kilograms is 18 ounces, or it's 1.12 pounds. So sometimes, a lot of times, I'd say we talk in pounds. How much refrigerant do you use? 2 pounds, 1.2 pounds, 1.8 pounds, 2.2 pounds, right? That's normally the more the lingo. You could say 5.510 kilograms. That's fine, but that's sort of like if I asked you how much the soda costs and you tell me how much it is in pesos. I could do the calculation, but I don't really care about what it costs in pesos. If we're measuring in pounds and ounces, kilograms is like pesos. Make sense? It's actually the metric version. So 0.510 kilograms is the same as 18 ounces, which is the same as 1.12 pounds. Okay, so that's how much we're going to put in. If it's the 2 liter, you can see it's a little bit more. 624 kilograms or 22 ounces, which is 1.38 pounds. Makes sense? So the amount of refrigerant that we charge is going to be per the sticker. So the real reason we use the sticker is to know what type of refrigerant, and even that's not mainly why we use it. If you start to do AC work, you start to learn the fittings. If you look at the fittings, you can tell what type of refrigerant it takes anyway. Okay. But you can also tell on the sticker. The main reason we look at the sticker is how much refrigerant should we charge it with. Make sense? When we charge it, we're going to pump 1.12 pounds into that 1.5 liter. Cool. That we will do. Okay. Now take a look here. If it's the hybrid electric vehicle, interesting. What that means is, like, let's say it's a Corolla hybrid. That's actually going to take the same R1234yf, and it's actually going to take the same amount as the 1.5 or the 2.7 in this case. However, look at the oil. You see the oil right there? The oil's different. The oil was a PAG oil on these two, but in the hybrid electric, it's a POE. So you can't use normal refrigerant oil in a hybrid electric. And the technical reason for that is PAG oil is not real resistant to conductivity. Right? It's a little bit conductive to electricity. So in a high voltage AC compressor, first off, a hybrid or EV is going to have electric driven compressor, and that's going to run on high voltage. It's probably going to be 3-phase AC. You can't have highly conductive oil inside of there because there's windings in the compressor, and you may get a phase to phase, almost kind of like a short, you may say. You may also get a high voltage to the ground, to the housing, which is grounded because it bolts to the block. You may actually get that. That would be an isolation fault, right? So if a hybrid comes in and you put regular PAG oil in there, it's not going to happen every time, but there are instances where the hybrid system will not power up because it'll sense basically a connection to ground. There should never be a connection to ground. That's called loss of isolation. You get a loss of isolation, you get the triangle of death, the car may not start. You'd be like, it just came in for an AC service and I charged the AC and now it won't start. Well, yeah, if you use PAG oil in a hybrid electric, that's exactly right. Okay. And then further, we got some warnings here. And this is a different one, not for the same car, but this calls for R134A, the cheaper, a little bit more old school refrigerant. And it's saying like with this system, with a single AC, it's 1.43 pounds, but with dual AC, it's 2 pounds. Anybody ever seen a dual AC system? It'd be like a big van or a big SUV that has front AC and rear AC. So mom and dad, or maybe, you know, dad and dad could have the AC on in the front, don't you be looking at me like that. In the front, the parents of unspecified parental preference would be in the front having the AC, and the kids in the back might actually have warm air on. Kind of makes sense. You can separate the two. Also on the dual zone, on the dual AC, if it's a big van, there's probably not going to be enough cooling in the front. You probably need additional cooling in the rear. And so we'll be kind of like doubled up on those. One compressor, one condenser, two evaporators. And because the extended lines and the second evaporator, they'll take 2 pounds rather than 1.43 pounds. Cool. So you're breaking down all the specs that you can get off that sticker. Um, and then kind of going more into strategy-based diagnosis here. And you guys have covered this in a previous chapter, but this is where it gets a little bit more diagnosis related. When you go up to this car, typically the customer doesn't come in and say, "Hi, I would like you to um, repair the open circuit in my blower resistor." That's not likely. What's more likely is the customer is going to come in and say, "Hi, my AC doesn't work." And you're going to really have to come up with a plan to diagnose that concern. And first off, we might have to ask quite a few questions because by default, the customer's going to say, "My AC doesn't work." They're not going to know. They're not going to like give you the details. Right. One of the first things we want to do is determine, is there airflow? If no, that may be like a blower motor issue. If yes, but it's warm, that may be, you could leave it open. It's up to you. Catch you later. That may be more like let's say it blows warm air. Maybe it's just, maybe there's no refrigerant. The refrigerant leaked out. It's got a leak. Um, there's a lot of different potential causes. So the point is, we want to get on this path of coming up with a strategy to perform the diagnosis, to get a good diagnosis so we can sell the correct repair. Make sense? The first time. What we don't want to do is, well, we'll sell you this and we'll try that, and then we'll try this and then we'll try that, because that's just not professional. That's not what we're trying to do. That's not what we're all about. We're trying to diagnose it correctly so we can give the customer a price that's a real price. Now, the price doesn't have to be cheap. I'm not saying it needs to be cheap, but it should be fair and it should be accurate. And you shouldn't tell the customer, when they say how much it's going to cost, you shouldn't say, "I don't know, you gotta try this and then it might cost more. We want this $1,000 repair. Is that going to fix it? I don't know. If it doesn't, we'll try another $1,000 repair and another." That's not right. That's not good. That's not right. That's not what this is about. All right. So drilling down, doing the strategy-based diagnosis, diagnosing it right, selling the right repair the first time. That's our whole entire job. Now, how's it going to start? Begin with the customer concern. How does it end? Thank you for that. Confirming the problem has been resolved. Okay. You guys with your drawing like little kids. I'm gonna fix that. You ding dong. If you draw in there again, consider yourself dropped. How's that? All right. Okay, and I can tell who does it. If I look at it, I can tell who drew that. All right, so talking about that strategy-based diagnosis, it's twofold. It should provide a consistent roadmap for technicians as they address the customer concerns that require diagnosis, and it should ensure that the concerns are resolved with certainty. Makes sense? So if you do the strategy-based diagnosis, it's going to give you both of those. Makes sense? And then obviously we could talk a lot about why the proper diagnosis is important, why you shouldn't bust out the parts cannon. If you bust out the parts cannon, you shoot a bunch of stuff and you charge a bunch of money, that's unfair to the customer. The other option is you bust out the parts cannon, you replace some stuff, it doesn't fix it. The dealership knows they can't charge the customer because the customer will sue them and they'll end up in court and lose. And the dealership ends up eating the cost of stuff, right? So it could be either way. Every misdiagnosis has a cost. It either costs the customer if you try to pull the wool over their eyes and convince them they should pay, or it costs the employer because the employer is going to eat it and not bill the customer. One or the other. There's really no in between. And if you're the employer, if you're self-employed, it costs you, sucker. But a lot of times if it costs the employer, like the dealership, if you say, oh, yeah, you need this part, and then you do the part and it doesn't fix it, a lot of times the dealer won't pay the technician. That's pretty common. If you misdiagnose something, they may pay you the first time, but if it comes back, they won't pay the second time. Or if it never even leaves, they may not pay that first repair. Sometimes they will, or it depends, but they may or may not pay the tech. Misdiagnosis is just not good. Now, what's this say here? The purpose of the state and federal laws is to protect the consumers, right? So this is especially important when the car is new and it's under warranty and they've got, lemon law protections. So if a car is dropped off and, basically the second it's dropped off, it's almost like a stopwatch. The stopwatch starts, and every day that customer is without that vehicle, it makes it further and further difficult for the manufacturer to win in court if they go to court for lemon law. Makes sense? So if it goes to lemon law and the customer's like, yeah, it was in service for 28 days, it's getting bought back. Even if it was for something stupid. Let's say that the customer said the AC blew warm sometimes and the tech drove it and it worked okay, and then tried again tomorrow and it worked okay, and tried again the next day and it worked okay. That vehicle being in the shop for those 3 days is not good, right? So now let's say it's even worse. They drove it 3 times, it doesn't work. You're like, you know what? Hey, I don't know what's up with it. Let's just replace the compressor. You replace the compressor, ship it back to the customer. They say, hey, 2 days later, it wasn't working again. I hit a bump and it works, and I hit a bump and it doesn't work. You put a compressor in. Imagine that one goes to court. And people are emotional. They don't always think logically. Sometimes they think emotionally, and they're like, oh, that car's a lemon. Yeah, they had to replace that part. It didn't fix it. They had to bring it back. Like, there's something real. That car's possessed. There's something really wrong with that thing. They replaced multiple parts, right? Multiple parts looks really bad. It's not good. Right. So ideally, we get the car in, we drive it. It operates normally. You compare it to another known good. You document that it's operating normally. You give it back. Now, if they really want to keep coming back and saying, hey, once in a while, my recommendation would be to kind of put some more of the responsibility on the customer and just say, look, we believe you. We're not calling you a liar, but we can't diagnose this unless it's happening. So if you can't help me make it happen and we can't make it happen, we can't fix it. Makes sense? And I wouldn't hang on to the car for a long time. And I've had many stories of having to go for a ride with the customer. And a lot of times, they're kind of like, oh, yeah, it's got this issue. And if you actually are willing to go for a ride with them, and you might, say, hey, it's noon, and by 12:30, hey, it hasn't done it. We can't spend all day just trying to get the car to be broken. If you get it to consistently act up, we can really fix this. Make sense? So a lot of this has to do with lemon law and buyback stuff. That's very, very common. Cool. And pretty much all the states are going to hold the manufacturer responsible. Was a new law. I don't remember what the bill was. California Bill AB something. Basically there's like, if a customer wants lemon law and they say um, June 1st, I want lemon law, the manufacturer has 30 days to respond with everything they need to respond with to be ready for like a hearing or a trial. Makes sense. So sometimes people can just say, I want lemon law. And if the manufacturer can't get their documentation straight within 30 days because they're busy, the customer already won. It's bought back. Even if there's nothing wrong, if they can't get their documentation straight, they're done. Right. So this is the direction everything's going. Sorry to let you know if you didn't know that. All right. So again, why do we need it so bad? It's challenging. Challenging's a nice word. It's challenging to find the source of every customer concern. I'd say it's full on difficult, right? Like I got in a debate with somebody earlier. It's a nice guy. Um, it was actually not even a car, it was an ATV. And he was kind of saying, well, once in a while it dies. Apagar, apagar. Okay, no problem. What's it do when it dies? And he kind of wanted to respond with, well, it's not a big problem. It's just a small problem. And I was sort of like, you don't know what the problem is. I don't know what the problem is. If you don't have a diagnosis, you really don't have anything. Make sense? The diagnosis is the most important thing, but it's also the most difficult thing. So if I were to tell him, yeah, replace your fuel pump, that replacing a fuel pump might not be easy, but it's not really complicated. It's just, you might have to, gas tank might be heavy or whatever, but if it was AC and I said replace the compressor, yeah, I mean, that's maybe not a super easy job, but you can see it, a start and a finish time. You can look at how much labor time it is. It's really just recovering on bolting, vacuum oil charge. Like it's not a real big deal. However, diagnosis can be. Sometimes diagnosis is simple, sometimes it's not. But diagnosis is much more difficult than replacing parts. Make sense? It might not be dirtier. You might not go home sore doing diagnosis, but brain power gonna have to be much higher with diagnosis. If we were to put it into um let's say like in education, sometimes we'll look at the we'll kind of look at like the difficulty level. So like remember is pretty low demanding uh, for understanding. So if I just want you to remember something, memorization is low. Um, to really understand it, to conceptualize, to diagnose, you have to have like a much, much deeper understanding of the system. And the reason that I want to point that out is with AC, it's real easy for you to be like, oh yeah, here's how you do the service. Here's how you do the recover, recycle, recharge. Here's how you replace the condenser. Here's how, whatever, not hard. But remember, most of the time the car comes in and what's the customer say? What have I been telling? What's the customer say? My AC blows warm. You got to really understand the system to be able to take the customer concern of my AC blows warm and be able to diagnose it and determine what you're going to sell. That's where the big skill's at, which is generally that's where the money's at. I know a lot of whiny techs are kind of like, well, Diag sucks. I'd rather just do gravy and stuff. Like, and I get that, but I've been telling you, there's been some people who have come through, and if they're good at diagnosis, they're making pretty big money per hour. And if they're really good at diagnosis, they can do a lot of diagnosis, and they're not tearing their body up. You know what I mean? So to get to the diagnostic level, you got to understand more than just the overview of the system. You really got to be able to understand what's happening in there to be able to conceptualize what would be the failure. Make sense? Cool. And then again, that's why we're really doing a strategy-based diagnostic system, right? We develop a procedure and a system to be able to diagnose it. And it's a new system and the systems change and they're difficult anyway. It's diagnosis gives me, it's a little bit more stressful because it's harder, which is part of the reason why I've somebody hires me to diagnose something and then they start telling me it's a simple problem, it's an easy problem. I'm like, nope, then you let me know what you want, what part you want me to replace. So I don't know. I'm not the mechanic. He said, oh, okay. Well, let me tell you how it's going to be. I don't know what's wrong with it. I'm going to have to spend some time with it, check some things. It's a process of elimination, right? That's what it said in the previous slide. It's a scientific process of elimination, not a replace one part. If that doesn't fix it, replace the next, right? It's like if I think it's the compressor, I test the compressor. If I think it's the thermal expansion valve, I test the thermal expansion valve. Make sense? Okay, and then additionally, if we got comebacks, customers are going to think maybe you didn't perform the work, right? Sometimes people are simple. They're like, oh, it's not fixed. You didn't even do the work. You charged me $1,000 and you didn't do anything, which is kind of sad because a lot of times technicians are trying to fix it. They just replaced the wrong part because their diagnosis was crap. Make sense? So they might think you ripped me off. You didn't even do the work, which that could be true, but I don't see that happening that often. I see misdiagnosis every day. I don't see people saying, I'm going to charge you to replace your compressor and just not do it. I don't really see that. Or it could be the shop is incompetent. And that one, that may be true. I mean, if you misdiagnose something, you're incompetent, but I would throw a whole lot of grace on there because it's hard to do a good diagnosis. And sometimes you're all going to misdiagnose. You're going to make a mistake and misdiagnose something. I'm going to misdiagnose something. We're all going to misdiagnose something. So I would probably say, like, I don't know about full on incompetent. Incompetent could really mean like you have no idea what you're doing. But my challenge to that would be, well, if I'm incompetent, find somebody else who can diagnose it every time easily. And they may not ever find anyone, right? So if the shop is incompetent, probably we're all incompetent. Everybody's incompetent. I mean, this is not easy stuff. It's difficult. So I probably more argue to say, hey, like, look, diagnosis is tough. That's the reason we charge more money for diagnosis than we do to do repair. It's just difficult. Okay. Or again, they probably think that the shop is scamming the customer. That happens a lot. All right, so now let's go through the diagnostic process. All right, first thing, you guys should know some of these. Step one, verify the customer concern. What's that look like? You guys give me a sample customer concern. Give me something.
Customer states AC doesn't blow hard.
Customer states AC doesn't blow hard. Okay. How would you verify that? Anybody? This is everybody's answer.
Turn the AC
Turn the
on
AC on.
hard.
And how you testing to see if it blows hard?
You turn the fan on to high.
Highest level.
Yeah, and then you're gonna kind of like gauge the amount of air coming out. All right, cool. I got a cool one for that. I just, I got a lot of friends at shops. This happens to be an independent shop, and he actually took AC with me, started his own shop way later. But lady in a Mustang shows up, says similar concern. I'm gonna change it slightly. My AC doesn't work. That's almost always what they say. My AC doesn't work. Like, oh, okay. He went out to the car and he's good. Technically he's good, but this one got a little sideways. He turned the AC on, put the speed up to high, and guess how much air he felt? No air. No airflow at all. So he's like, "Oh yeah, I got it." Did some diagnosis, found that the blower motor didn't work. Checked for 12 volts in ground, the blower motor had it. Double checked himself by applying 12 volts in ground, the blower motor still didn't move. Put a blower motor in there, all of a sudden, blower motor works. Car's done, right? So he just shipped it real quick. She took the car, came back and like, the AC still doesn't work. And he's like, I verified it was fixed. And then she's like, well, it blows warm. And he said, well, before it didn't blow at all. And now it blows air. She said, yeah, I agree. It didn't move air at all. And now it blows air, but the air is warm. It was still a bad situation to be in, right? So we always have to start with verify the concern. And in this case, he kind of did. And where he might have fallen off a little bit later is the verify repair. And we'll come back to that. So if we were to look again at the verify the concern, you got to understand it first. So if the customer states the AC doesn't blow hard, you were probably really looking at airflow, but I would still back up a little bit and check like, does it blow ambient temperature? Is it blowing hot heat? Is it blowing cold air? Is it blowing on all the different speeds, right? Because honestly, the customers just think like my AC doesn't work means you're going to like take an AC out and put an AC in. The AC is not a unit. It's all these different parts. So when we do a repair, we're not changing the whole unit in a similar way to where a home would be. Like if you had a ductless AC system and you say, hey, it doesn't work, they're going to show up and rip all that junk out and put a whole new unit in there. So it doesn't matter if the blower worked or not, or if it blew warm air or cold air. It got a whole new system. That's not how automotive works. Make sense? So he addressed the airflow issue, but overlooked a different issue that was causing to the warm air. Make sense? All right. So how we verify it, I think we're probably pretty good. The next thing we want to do is research possible faults and gather information. So even me right now, if I get a vehicle in with an AC concern, I'm gonna kind of back up a little bit and just, you know, I may do some basic testing, but a lot of times I'm gonna research and gather information. Are there TSBs? Was there any work history, performed recently? Um, Another thing I may do that's kind of within the system is the compressor running, right? All I got to do is look, is the compressor running? If the compressor is not running, that's taking my mind in one direction. If the compressor is running, but it's blowing warm air, that's taking my mind in a totally different direction. So give it a good overview, right? Don't jump in there like rookie techs. A lot of times what they'll do, they'll be like, oh, the AC doesn't work, hook the machine up, hit recover. And you're going to pull the 2 pounds out of the system and be like, oh, well, it had refrigerant in it. All right, cool. But you wasted all that time to verify that there was refrigerant in it. That is not how a more well-seasoned technician would start. Even though I'll confess, 8 out of 10 cars that have warm air concerns probably have a leak and they're probably low on refrigerant. I still wouldn't waste all that time doing that process. I'd take a step back. I could even just as simple as this, feel the temperature of the lines and know if it's got a decent high and low pressure without any tools, just with these tools right here. Okay. Or if I wanted to step it up a bit, I'd put some gauges on there. And my gauge pressures will actually tell me if the system is charged or not. I don't need to do a whole 30-minute AC service to tell how much refrigerant is in there. That's not the first step I would do. Right. So loosely doing an overall to determine which way you're going to go. Let's say that compressor didn't run. You may get the wiring diagram out. You may do an overview look of what components could cause the AC compressor to not run, what the circuit's life. And then, of course, we're going to do step 3, the focus testing. And that's where we're going to do more, even putting the gauges on there might be more considered focus testing. Sometimes you blur the lines a little bit, but if the compressor doesn't run and I got the wiring diagram and I check the relay and the fuse and I check to see if it has 12 volts and ground at the compressor clutch, that's focus testing. Makes sense? That's actual pinpoint tests. Cool. Let's just say I check the compressor and it has 12 volts and it has ground, but that magnetic clutch doesn't actuate. I know that the magnetic clutch is no good. Most likely, we're probably going to replace the whole compressor assembly. I'd say, hey, I diagnosed this. I checked here. I checked this. I checked this. I measured this. I measured that. It's a defective compressor clutch. Recommend replacing the AC compressor. Of course, step 4, you're just going to perform the repair. If you perform the repair and step 3 was correct, you do the diagnosis right, step 5 should be easy money. Step 5 should be like, yeah, I put the new compressor in, vacuumed it, oiled it, charged it, and I verify the AC works. It blows cold in all speeds, everything is good. Nice job. Now, what the guy told you about with that Mustang, what he didn't do, he felt it blew no air. He diagnosed it as a blower motor. He put a blower motor in. He felt it blew air. He shipped it. What he didn't really do is like, wait a second. let me make sure it blows cold air. If he were to have checked that, he would have called back and said, hey, it's kind of weird. It was blowing no air. We replaced the blower motor. It's blowing air, but you know what? It's just, there's another issue. That's fine. Okay. That's fine. It's maybe not perfect, but that's not bad. And then you'd say, well, I thought that was going to fix it. And you could at that point say, well, the first thing I checked was the airflow and it had no airflow. So the fan motor was not working. I got that fixed. I correctly diagnosed that. I fixed that. But part of my job is to verify the repair. And I did verify the air flows now, but it's blowing warm. And the customer is going to say, well, I want it to blow cold because it's summertime. Makes sense? They'd say, I understand. I need to diagnose that and I need to charge you additional money to fix that. And they might have a little bit of a fit, but I think you could explain it pretty cleanly. Like, hey, you got at least two issues here. I diagnosed the first one for you. That's how much you owe me. We got to look into the second issue. And that would have been legit. Unfortunately, what this guy did, he verified that it blew air. He shipped it and the customer left. And 5 minutes later, they called back like, hey, my AC's not fixed. And then, his dad owns the shop. So he's sort of like, hey, what happened with that thing? What'd you do? What happened? It's misdiagnosed. The customer's on their way back. She sounds pretty upset. She came and picked up her car and paid her bill and it still isn't fixed. It was ugly. So partially it was actually a good diagnosis. It just wasn't a very thorough step 5. Step 5 would, if it's not repaired, you got to go back to step 1. And sometimes your diagnosis was correct and it just has multiple issues. Or other times your diagnosis is incorrect, and that's probably more likely. All right. And then from there, remember, we got to write it up. Remember the 3 C's, the concern. So like if it was the AC one, it'd be like your customer concern was AC doesn't blow hard. The cause. And now let's just break down the concern first. The concern is the main focus. So that's what's written on the repair order. The customer concern should say, like I got one right here. The customer concern is telling you why they're there. I noticed now as a technician, I didn't really talk to customers, but now I'm doing some stuff, on my own and on the side and whatever. I noticed customers need some coaching. So when I talk with the customer and they say, oh, my AC blows warm, it's going to say like, all right, well, does it always blow warm or did it happen recently? Like, was it blowing cold and then all of a sudden, boom, it blew warm? Or did you feel like it was blowing cold, then it was blowing cool, then it was blowing kind of cool, then it was blowing kind of warm, and now it's blowing full warm? You know, anybody think they know why I would ask it like that? Do you see what I'm driving at if I ask it like that? Was it a gradual failure? If it was a gradual failure, what do you think my thoughts are? Sounds like a leak to me. Right? If it's a gradual failure, it sounds like a leak to me. If they're saying, oh, no, no, it was cold in the morning and then on the way home it was warm, I'm thinking like, maybe not, right? I mean, but the customer concern guides the whole process at the beginning. We got to make sure that we get a good concern and we got to make sure we address the concern. And sometimes they're kind of funny, like, they may not word their concern very well. And so if they say my AC blows warm, and well, I'll apply it to a specific example. I had a dude show up with a Silverado back in the day at the Chevy dealer, and he said, yeah, my AC doesn't blow cold. I jumped in the car in the Silverado and I noticed a couple details. I'll come back to those. And I was like, this AC it feels cold to me. It's colder than my truck. I could have just said like, nah, your AC is good. Ship it, right? I could have. But to be thorough, I said the concern is the AC doesn't blow cold. I actually measured the temperature. I compared that temperature to another Silverado. His actually blew like a couple degrees cooler. And I just said, no, this is good. I can't verify this concern. I did not attempt a repair. Make sense? And this one was customer pay though. He bought it used. And then I remember letting it go and he came back and he said, hey, same concern. And the service advisor gave me a little bit of attitude, was like, hey, it's back again. It's still blowing warm. And I was sort of like, remember, look at my notes. I wrote down it was blowing at like 54 degrees or 52 degrees or something. And a kind of high humidity. And another known good was blown at like 58. Like, there's nothing wrong with the AC in that truck. And he's sort of like, well, he says there is. So again, I'm listening to the concern. I'm saying it's AC blows warm. And I said, let's press on him a little. It blows warm like when? So I did. That was my next step. Talk with the customer. And there were clues. Okay. So when I got in the car, it felt like the seat was kind of worn out and there was a seatbelt extender. You ever seen those? It's if you're so big you can't get the seatbelt buckled, you got to get a little extender, right? So this was a well-fed boy. He was a hefty fella, if you will. And I was like, this might have something to do with this concern. I'm not trying to be, harsh or, like no body shaming. I'm just more saying like, okay, I'm trying to piece the clues together here. So I said, hey, let's talk with this customer. And so I pressed him a little like, hey, I measured your AC. I measured the actual temperature. Your AC's blowing nice and cold, colder actually than the truck I compared it to. And he said, well, I still feel hot. And I was sort of like, dude, I gotta tell you, I understand you're not happy with the way the AC blows, but your AC is operating normally. You understand? Now, what do you think I could fix on that car? Nothing. I could fix nothing. If that thing is blowing the temperature it's supposed to blow at, I'm done. That's it. There's nothing I'm gonna do. And he's like, well, you think you could do the service and get it to blow a little colder? No, no. I mean, I compare it to a known good. It's good. Like and I could take it a little step further. I could check the pressures. The pressures are in spec, the temperatures in spec, everything's in spec. That's it. If you're not happy with the performance of the AC and you still feel hot, I guess it you probably should have bought another vehicle. I mean, this is normal. And I'm not sure any vehicle would really make this guy happy. I think I know what would make him feel better, but I'm not a doctor. I'm just saying, when you need a seatbelt extender, you're probably going to feel hot. And so it was, and then he actually came back a third time, even after that. And he's like, yeah, I really need that AC fixed. And I was sort of like, what makes you think there's a problem with this AC? I mean, you've been back 3 times. Like, what do you think is really wrong? Well, I had my Dodge Dakota and I felt like it blew colder. And I was sort of like, okay, dude, this is not a Dodge Dakota. I can't make it work like a Dodge Dakota. Like, I can't take an AC system from a Dodge Dakota, put it in here. To be quite honest, I don't actually think the Dodge Dakota blew cooler. I don't know if it was more like a who knows? Some with the seats. Maybe the Dodge Dakota had tinted windows and the Silverado didn't. I don't really know, but I'm more just saying like you got to be really on top of that customer concern. And in the case of the Mustang, you know, that customer concern was vague, and in a way, it led him down the wrong path. It was actually the AC didn't blow any air and it blew warm. I'm just not sure that the customer knew that, right? So a lot of focus to be done on the concern. Make sure you're after the right concern. Cool. And then as we get more in the cause, this one I got a couple additions to do. When we're talking 3 C's, the when we say cause, we mean the cause of the customer concern. Okay. So the customer concern was my AC doesn't blow hard enough. The cause is where we're going to write up our story of what we've tested, how we've tested it, documenting the tests, where we tested, what the reading was, all that type of stuff. Our story goes in the cause. And then we may say, let's just say the blower motor was defective, kind of like this one, right? The cause was the blower motor was defective. Now that's the cause of the concern. Now, what I wrote right here was something that I want to add in right here. Look, sometimes from a manufacturer warranty perspective, this can be a bit more complicated, right? So I've been talking with people at the region and stuff. If a part failed, the cause is likely to be unknown. So let's just say like it was that blower motor or a temperature sensor. Sometimes what they can mean by cause is what caused the part to fail? Do you know what caused the blower motor to fail? Do you know what caused the sensor to fail? And the truth is, like, as technicians, generally, we probably don't know. And and that's okay because that's not really the focus of our three C's. We're mostly focusing on the cause of the customer's concern. Make sense? We're not trying to say that the blower motor failed because of excessive voltage variation in the system. Like, that's not, we're not trying to do that. We're just trying to say the blower motor failure was the cause of the customer concern. AC doesn't blow hard enough, right? That's it. Cool. The reason I added this was because sometimes when we're doing our CCR, if it's Toyota specific, the remedy, they may want you to document what caused the failure of the part. And I'm going to tell you, you probably don't know. You might know, but you probably don't know. Make sense? So we'll focus mainly on the three C's one more time. Customer concern, the cause of the customer's concern, and the correction, which is, how you repaired it, what you repaired, but then also how you verified the repair. Make sure you can list how you verified the repair. Okay, that's the way we're going to do it. And then we may call that the remedy. Okay. So if you get into stuff with TAS and or some kind of technical assistance and factory stuff and holding parts to be returned to the factory, we don't exactly know why those failed for the most part. You just don't. An engineer might. An engineer may very well study that failure in detail under a microscope and find out the exact failure point. And actually, I'd like to add a detail. Do you know why they're so funny about the cause right here? I'm gonna teach you something that I didn't know as a technician. I've only known more like later in my career. Toyota, do you know who makes a lot of their components, electrical components? Say like a O2 sensor. Let's say a AC pressure sensor, even like an AC compressor, probably.
Denso.
Denso, exactly. So if we pick Denso, so if Toyota sells 2026 Camry, make it 2025. 2025 Camry, and that AC compressor fails, yes, you bring it to the dealership diagnoses it, the dealership puts a compressor in there, the customer pays nothing, the dealer does the work, and then the dealer bills Toyota, right? That's the depth of what I knew for like 15 years of my career. Do you know what happens after that? Toyota sends that part back to Denso with an explanation of the failure, and Toyota bills Denso. I had no idea, right? So if the vehicle manufacturer uses a vendor such as Denso or whatever, Bosch, they actually bill the stuff back to the part manufacturer. So Toyota is going to use some of your documentation, and they're probably going to add some more, especially when they're trying to get down to the root cause of it. Your documentation is going to get your dealer paid by Toyota, and your documentation may very well get Toyota corporate TMNA paid back by Denso, however that I don't know a ton about that, but I know that that's how it works. Okay, so part of the reason that I added this is because a lot of times the engineers want to actually know why the part failed, and that's a little bit outside of what the technicians do. That's more where FTS functions, or like some manufacturers would call that like a field engineer, that type of people. That's what they're doing. They're slaying the big dragons. We're just slaying the little dragons. All right, cool. And then the repair order, of course, you guys know all the details, the documentation, your steps, all that stuff has to be documented. So in this class, we're going to do a lot of diagnosis, and we got to get those three C's dialed in. I'm gonna help beef you up on your three C skills. Some of your technician stories were great, and some of them were all right, and some of them were like they're a work in progress, just like us. Cool, pretty fun. All right, now history. This one's pretty fun. We don't have to go into crazy detail because it's not important for you to know how to fix the old stuff, but it's cool to get a perspective of where we came from. All right, so what's the definition? HVAC, heating, ventilation, air conditioning. So if I say HVAC, you know what I'm saying. I'm talking about heating, ventilation, air conditioning. It must provide the desired vehicle passenger climate in all types of weather. If it's cold, we want heat. If it's hot, we want AC. If it's whatever, if it's smoky outside, we want filtered air. Make sense? We want the air to be conditioned. Okay. So like typically in a modern vehicle, the engine's cooling system is used to heat the vehicle interior. So if we have a car with a no heat concern, and we will spend a day on heating systems is not that complicated. AC, we're going to spend a few weeks on, right? But the heating system from the perspective of HVAC is to make the air warm. It's the same parts as the cooling system for the engine. We're just looking at like the opposite side of the same coin. So if you have an engine that's overheating, you're looking at like maybe it's a fan, maybe it's a radiator, maybe it's a leaking coolant or whatever. If you have a vehicle that's blowing not hot enough heat, you may be looking at the fan running too much. You may be looking at the thermostat stuck open. You may be looking at a coolant leak, right? So it's the same parts. It's just from the other perspective. And we're looking at them in a little bit of a different way. Like an overheating concern is more of an engine concern, but an underheating, so that'd be a vehicle that never gets up to full operating temperature, that's not really an engine concern. That's an HVAC concern. Customer says, hey, my car doesn't blow warm heat. It blows kind of cold and my windshield's fogging up and my windshield's icing up and my passengers are freezing and stuff like that. Like that's actually probably an engine cooling system issue, to be honest with you. Okay, so kind of neat. And then it's also um for AC, we're using an engine driven compressor with a belt to circulate refrigerant. It's going to cool the interior. We'll get more into that. And then a lot of times we're using some sort of cabin air filter, maybe a paper filter. Sometimes it can have like charcoal impregnated filters that's going to help with odor and stuff. But it should definitely minimize the dust. Although, you know, they're they have higher end ones that are ionization and stuff. Like they do okay with dust. You can also buy HEPA, you can buy, upgraded filters and stuff, but some of the filters are pretty basic, but it's better than nothing. Cool. So the process of maintaining comfort for the occupants by conditioning the air with regard to temperature, humidity, control, output, and cleanliness. That is what HVAC is right there. How we add or remove heat and humidity, clean the air of dust, pollen, and odors, controlling a source and the output of air along with the direction, controlling the velocity of the air through the HVAC system. All right, hold up. It's a lot of stuff right there. Adding or removing heat, let's just start with that. If you want heat, where's the heat come from? What do you think? Probably going to come from the engine, right? From the hot coolant, would you say? What if you want to remove heat? How are we going to do that?
Goes through the condenser.
Yeah, exactly. We're gonna use the whole AC system, compressor, condenser, evaporator, all that. Yep. And both of those remove humidity. So that's what's kind of interesting. If you have windows that are fogging up because you're having a really in-depth conversation with your friend and the car's off and you're parked and the windows are up and you get a little too heated in your debate about politics, next thing you know, the windows are all steamy and fogged up. You need to remove humidity, or the windows aren't going to be clear. How do you remove humidity? You can either heat it, and that'll remove humidity because it'll kind of like burn the humidity off the hot heater core. Or, believe it or not, you can actually run the AC, and that AC will get cold, and the water in the humidity, the water, the moisture in the air will condensate onto the evaporator and drip out the bottom of the car. Both of those remove humidity, so you know. Cool. Now, cleaning of dust, pollen, and odors, what system you think does that? What part? Cabin filter,
Cabin.
right? Bingo, got you. Very good. How about controlling the source and the output of the air along with the direction? That's a tougher one. I call that the HVAC box. That's got all the doors. It's going to send air where you want it. It's going to make the air go to the windshield or to the face vents or to the floor vents, right? Or to a mix combination. So we'll call that the whole HVAC box. Sometimes they'll like air handler, or they have a lot of different names. The black box behind the dash. Okay, what about controlling the velocity of the air through the system? What do you think is going to control that?
The fan switch.
Exactly. So when we're talking blower motor and the blower fan, those kind of interchangeable sometimes. The motor turns the fan. A lot of times we'll call it either the blower fan or the blower motor, right? But to change the speed, we got the switch. We probably have like a resistor. We might have a transistor. We might have a control module, but that part of the system works with all these other parts of the systems to do all those things that we want it to do. But when a car comes in and you turn it on the high speed and it gets no air, you don't have any business checking the heater core and checking the thermostat and checking the refrigerant level. Like if it's blowing no air, get down here to the blower motor and the associated circuit and components, right? So just giving you like a little overview. Cool. So back in the day, we actually had cars. If you wanted to heat your cabin, believe it or not, you could actually use exhaust gases. So they would run exhaust sometimes through the interior, put little fins on it, put little heat shields, put little tin warming things. They even had heating elements, electric heating elements in the steering wheel. Those made quite the comeback. But they did, start with open cab vehicles. We then moved to the closed cab vehicles. So we started looking at warmed stones, heating oil lamps. I mean, does this sound scary or is this just me? It's like you can have a bunch of hot stones right there to warm your hands. That's how we used to dry our gloves when I was a kid when we came out of the snow. It'd be like put your gloves on the radiator or the boiler or whatever, depending on how you're heating your house, right? That was some janky stuff right there. That's how they used to do it. Imagine going around with a heating oil lamp. Getting a little fender bender, heating oil lamp falls over, catches on fire, burns you inside the car. I mean, this is a disaster. But by the 1930s, we had some basic air conditioning. Um, what it really was evaporating water. Interesting. Has anyone ever heard of a evaporative cooler? There's a slang name for it.
Like a swamp cooler.
Bada bing, bada boom. How you doing? Yeah, swamp cooler. So we'd literally have air come up into this device, and the air would hit here, and right in there we'd have like an element that we would get wet. We'd have run water to, or we'd get it wet, and the air coming out of it would blow into the window, and it would actually be cooler because of the evaporation effect. So if you were to have a dry heat and it were the drier it is outside, the lower the humidity, the faster it'll evaporate. The more it evaporates, the more it cools, right? So actually for Southern California, this would work decent. For Florida, this wouldn't do anything at all. But in the West, we got lower humidity. This evaporation, very rapid evaporation, could actually drop up to 15 degrees difference. So you'd put the window down and this would scoop the air in there, but it would run through a cooler. It would evaporate across an element. There'd be water running down almost like cardboard. Cool. So they still do swamp coolers, just not in cars. We actually will maybe rig up a swamp cooler for summer class because it's going to be hot. Cool. That was the beginning. I mean, that's pretty cool. If you go to a car show and you see one of those, now you know what that is. Right. And then if you go a little further, we had the first known vehicle with mechanical air conditioning was a 1930 Cadillac. Ooh. And it had a standalone system installed in the trunk, and it ran off of gas, but it had its own gas engine in the back. So you'd have to pop the trunk and put gas in the engine and start it, and that would be running in the back. Brrr, and that could actually give you AC. It's pretty nuts, right? But a cool system. So 1930, and then that was called the Kelvinator, by the way. And then a little bit later in 39, Packard came out with a vehicle that had AC that was a little more traditional. So if you want to look at that as a cutaway, this is pretty similar to how we are now. If you look, we've got a compressor, a belt, a condenser. That compressor is going to circulate the refrigerant. You can see the refrigerant will come into the compressor. It will go to the condenser, leave the condenser, go through this weird little receiver, and it would go all the way to the back of the car where it had an evaporator, a blower, an expansion valve, and it would blow the air up the roof and down the floor and eventually cool it. This is actually not a horrible system. Better than the Kelvinator where you had to start the engine in the back. So this was nice because it ran off of the engine with a belt running the compressor. So by 39, they had started to kind of figure it out. Still a little crude with the whole thing in the back and all, but not horrible. They didn't think to make any room up here. There's never a lot of space right there. That we've of course got the big HVAC box there now, but they didn't figure that out for a long time. Okay, and then in 54, Nash and Pontiac had kind of a similar one to this Packard system, except it had dash mounted controls. So you could actually engage the compressor by pushing a button or like by closing a switch, I should say. Okay, so that was pretty cool. Here's what that looks like. Right, so you can see it looked kind of similar, but it was more front mounted HVAC. Then for a while they were up under the hood and stuff, but you can engage and disengage this one electrically. See, it's an electric disconnect switch. That was a cool system. Right. And then we went over in 57 from R22 to R12. So some of what today is going to be is talking about the different refrigerant types. It's not the most exciting thing in the world, but you should know some history. R22 was used in houses for quite a few years after that. But in cars, the problem is we crash them. So we've been constantly looking for a refrigerant that's going to be, well, there was cheaper, but then it got into like more environmental concerns, and we'll get all sorts of deep into that today. But they were changing pretty regularly. And then what was pretty cool in a couple pictures, the 63 Corvette became the first sports car with air conditioning. Right. So like before 63, there was no sporty cars with AC. There just wasn't, unless you added them. Cool. So there's that other type of system. There's that sweet rear end of that Corvette, I would say. So that's 63 right there. That was the first Corvette that had AC. Cool. From there, in 67, GM came out with this thing called the air mix system. So the air was passed over an evaporator. Ooh, interesting. Which would cool and dehumidify the air. Then a heater core to heat it. So basically, you'd heat and cool the air. But what that would mean was before this moment, you had heat or you had AC. And when you had heat, it was all the heat. And when you had AC, it was all the AC. But now this could actually mix the airs. So if you wanted like warm air, but not hot air, it would actually cool the air and then heat the air somewhat, and you'd end up with warm air. If you wanted really cool air, it would bypass the heater core and go just to the evaporator, and that would give you the coldest air, right? So it could fine tune the amount of heat. The hot air going through the heater core and the cold air going through the evaporator, you could control the volume of how much of each of those air would get put into the passenger compartment, and that would fine tune it. It was pretty neat. Cool. And then you'll see that was like top of the line for a long time. Then 20 years later, in 1987, we had this thing come out called the Montreal Protocol. And so they said, hey, you know what? R12 is bad, and we'll get into why. And I'll actually prove it to you. But they got together and they said, you know what? We're gonna phase out R12. R12 is just no good. And then by 90, so just a few years later, did you know 94% of the vehicles were produced were equipped with AC, right? And that's when the Clean Air Act was passed into law. So they started kind of looking at the AC being, causing some issues. And then just a few short years later, they did pass the new Clean Air Act. but there also was a big increase in how many cars had AC around that time. So before 1990, a lot of cars didn't have AC. Before 1980, even more cars didn't have AC. In the 70s, a lot of cars didn't have AC. In the 60s, most cars didn't have AC, right? So it was getting more and more common, but they're also knowing that that R12 was causing some issues, right? And so in 2010, Union mandated any refrigerant with a global warming potential of more than 150 could no longer be used. So we did a big jump there. Now in 2010, they're like, hey, a global warming potential of 150, no good. And the US, followed suit. And pretty soon after, the US Climate Action Plan of 2015 said R134A is unacceptable as a refrigerant vehicles past 2021, right? So that just gives you like a skim of the history. We'll get into all the different legislation that's actually part of today, to why we went from the R22 to the R12, from the R12 to the R134A after the Montreal Protocol. And then after that, Europeans were like, hey, R134A is not that good. And then it took US a little longer, and they're like, hey, in 2015, they're saying R134A is out. We're going to make them use something else. And they weren't even totally sure what it was going to be. That obviously ended up being R1234yf, which is the only refrigerant that they're using in cars now. Because look, 2021 and up, you can't be having R134, even though it was a fourth of the price. You got to pay 4 times as much for the YF. We'll show you why. So changing, we're getting into safety a little bit, and then we'll get into the more technical aspects of refrigerant types and some of the legislation and the policies and stuff like that. So when we're working with HVAC, remember there's some safety things we have to be worried about. And if you're exposed in a weird way, if you really want the facts, remember, you can always refer to the SDS, what used to be the MSDS, just the safety data sheet. It'll tell you about treatment, it'll tell you about exposure, it'll tell you about all that type of details. So if you're working with a R1234yf and you have an issue, all you got to do is look up a SDS for R1234yf. It'll tell you all the protocols depending on what it is you've done. If you've ingested it, I actually don't really know what to do. But generally, you just don't really want to get it on your skin, mainly because it can cause freezing and literal frostbite, these types of things. It's not the most dangerous thing in the world, okay? But of course, we're going to use PPE, for example. Hand and eye protection, they recommend long sleeve shirts, the correct types of gloves, eye protection. Remember, if the refrigerant escapes the system and contacts the skin, there's such extremely rapid evaporation, it can actually freeze. It'll freeze your skin, and it could cause instant frostbite. So I did have a student at one point, they didn't recover the system correctly. They went to pop a line off. The refrigerant got like kind of sprayed out onto his hand, and he's like, "Ah, it burns. It's hot." And I was like, "That's not heat, dude. You're getting frostbite right now." So we had to, run his hand under some warm water, and he thought it was a chemical burn, but it's just the rapid evaporation is literally freezing your skin. So with that being said, keep this in mind as we work with this type of thing. There's a safe way to handle it. So we're going to, of course, do what we're supposed to do and handle it safely. But the PPE is still a good idea because, once in a while, a hose is almost torn through and you move it just wrong, and all of a sudden, psh, and you're getting sprayed and stuff. Okay. And of course, in your eyes would be really bad. So if you were to get a direct refrigerant discharge into your eye, it will blind that eye. So we're going to be making sure everybody's using the correct PPE. Cool. And then again, depending on the vehicle, there can be some different specific safety hazards. Like for example, if it's hybrid or EV, that might be AC PPE, but also hybrid and EV PPE, those types of things. But generally, if you're dealing with HVAC, this is going to be pretty similar. Another thing to be worried about is ventilation. Part of the reason why ventilation is because, like what we see right here, if the refrigerant gets out, it's colorless, it's odorless, and yes, it's considered non-toxic, but if it's gaseous and it settles in the air, it displaces oxygen. It's heavier than the air, so it tends to lay low. If it displaces oxygen, what do you think this word means? Asphyxiation. It's like you're
We can no longer breathe.
exactly. You're going to be breathing, but you're not breathing oxygen. You're going to be breathing refrigerant, and refrigerant will displace the oxygen. So it's like it's not exactly like drowning, but it's like you're not getting air, you're not getting oxygen. There is no oxygen because you're surrounded in a low-lying cloud of the refrigerant. So again, that's why we're worried about ventilation. Okay, so if you feel like you're not breathing, get out of there. Walk away, go outside. By the way, when we're really working on this, we're recovering this stuff. So if you're popping a line off and discharging it in your garage with all the doors shut, you may experience some of this. We're not going to do janky stuff like that. We're going to do it the right way. You're not going to even experience this, but you still need to be aware this will displace oxygen and cause you to get no oxygen to your brain, and you'll die from that if you do it. Okay. You won't die instantly, but if you were to stay in that environment, you would die. Cool. And then we talk about like using a torch, heating or something. We got to be we really can't heat the AC system. You can't be having an open flame around the AC system. You just can't do that. And same with the tank and the gauges and the lines and stuff. You just can't do that. Okay. Now, here is something that usually gets people kind of interested. Most automotive refrigerants are considered non-combustible. However, when mixed with a certain amount of air in the right circumstances, they can become flammable. So, like for example, R1234yf is flammable. It's kind of like gasoline. Like you could throw a match in liquid gasoline and it won't burn, but if the gas is vaporizing, you have fumes and vapors, it can. It's similar, and especially with the 1234yf, the latest refrigerant is more flammable than any of the others before. Make sense? So you just got to be aware with, smoking or torching or these types of stuff. You just really can't do that, especially when there may be any kind of leak or something. Okay, makes sense? So when we go to work on it, we're going to completely recover it for our safety, but also when we get into it, it's actually illegal to discharge that without recovery. So you need to do it for the environment and for your safety. You definitely need to do it. Cool. And then storage containers, just FYI, we don't ever fill them over 60%. The reason why that container, picture like a propane tank. Propane tanks, we do the same thing. It's going to be in liquid form, and then we need a little area in the top where, it's if it can expand and contract, it'll also be a vapor on the top, and we're going to pull vapor from the actual top of the tank and stuff. You can't have it 100% charged because as it heats and cools, it'll increase and decrease pressure. We need to leave some basically space in there. That's what I would say. Right. So the thing is, if you were to do the discharge into your own tank, because let's say you go into like mobile HVAC, you need to know that if it's a 10-pound tank, you can only really fill it to 6. But in what we don't really do with our HVAC machines with the full, $4, 5, 6, $7,000 RRR machines. Yes, I said RRR. Those are not going to let us overfill the tanks. Those know how much is in the tank. It won't let you overfill. Generally, we start with full and we're charging cars. We're not discharging a lot of cars anyway, so it'd be a little bit weird. But the other thing is refrigerant that you buy at the store. Let's say you have our machine, or you buy gauges and you want to just do manifold charging, you can. If you go and buy the machine to charge it, that's going to be disposable. So the disposable container is not made for recovering. It's just made to charge the car. It's not made to recover the car. Makes sense? So if it's like the little blue one for R1134A, you can't use that as like a recovery tank. They also have a check valve, so you literally can't. You actually it won't work. Okay, but they're not made for that anyway. Cool. And then remember, we're talking about gloves. So this is going to be a new word for you, barrier gloves. So what a barrier glove is, in the latex and nitrile, they may work okay, but it needs to be a barrier glove, which is going to be like a chemical barrier, a fluid barrier. It If you have mechanics gloves, right? They call them mechanics gloves, and I always think like, I don't know, why are they mechanics gloves? Like mechanics glove is not going to protect you against half the chemicals, the oil, the coolant, the refrigerant. They're not really mechanics gloves. If you're working with refrigerant, you need a glove that's impermeable. It's a barrier glove. This would be the glove to use. The refrigerant can't get on your skin and cause that frostbite. Cool. That's a barrier glove. These ones are nicer and longer sleeve and a lot thicker than the nitrile gloves we commonly use. Cool. But again, watch before you service the AC system, check the manual. A lot of times they'll have, some warnings and some hazards and some details to make sure you know kind of what you're getting into. Also, we shouldn't really be reusing O-rings. Refrigerant oil's hydroscopic. So what that means, well, same as brake fluid. You can't have refrigerant oil just sitting out chilling. It's going to absorb moisture. We have it absorb moisture really to keep it out of the refrigerant flow. Okay. It goes into the oil, and so the oil can kind of capture it better, but you you should really be coming from a sealed container when you add oil. Okay, that's the deal. Don't open it and leave it out. Cool. All right, any questions on that before we get into your favorite part? Environmental and legal concerns and responsibilities. This one's a fun one. I think so far pretty straightforward. And this one, we're not going to even make this one really super complex. Keep it kind of fun and light. I'll make some silly comments to keep it interesting. Here you go. Let me get you, train you all up as climate activists. You can go join Greta. So, back in the day, which wasn't that long ago, scientists theorized and discovered damage to the ozone layer that surrounds and protects the Earth. You guys have heard of this, right? If you haven't seen Captain Planet, we just can't be friends, right? Captain Planet, do you know? No. Abner knows. Rotseni, I think, knows, but some of you probably don't even know what Captain Planet is. Okay, so optional assignment: watch one episode of Captain Planet. You could also get half credit for watching Disney's Fern Gully. Okay, but here you go. They figured out there was damage to the ozone layer. Now, what is ozone? Ozone is composed of 3 oxygen molecules. So, oxygen like typically is O2, right? But ozone is O3. So it's not really that different than oxygen. It's just 3 oxygens rather than 2 oxygens. It's part of the atmosphere. Now there's 5 layers, okay? So troposphere, stratosphere, mesosphere, thermosphere. Let's take a look at those. Look at this. This is Earth. You are here, okay? About 7.5 miles troposphere. And then the ozone layer really varies. 9 to 20. Then we got the stratosphere. What did we miss there? Mesosphere. Okay. Sure. Okay, so you got a few things going on here. Exosphere, right? We got a bunch of layers. The important one is check this ozone layer out right here. Above the troposphere, we should have this ozone layer. It should be around 9 miles from the Earth and up to 20 miles from the Earth. Okay, that's the ozone layer. The ozone layer is not like a big like the what do you have when it's some of these video games when you can put up a shield and no missiles and stuff can penetrate? What do they call that? shield. What do they call it? Somebody knows.
A
Like a-
barrier?
Force field?
Yeah, yeah, it's not a force field or like it's not like that. It's literally just right here. The ozone layer should have a lot of that ozone. It should be a whole bunch of O3 molecules. That's it. It's not like a big plastic shield or a bubble or a easy up or something. It's just a layer that should be a bunch of O3, should be ozone. Now, what's the reason this is important? You ready? That ozone layer, it's like oxygen. Remember, it's O3. It absorbs ultraviolet radiation, so UV. Um, especially UVR wavelength. So there's UV that could be, I don't know about full on good, but like there's UV that we could deal with, and then there's some wavelengths that are like really bad. UV causes skin cancer. That's really bad. It does cause sunburn. You guys are gonna notice I am like red. You'll see. Been outside too much leading up to summer class. Damage the eyes, damage it'll really damage anything. Like if you leave something out in the bright sun for a while, it's just gonna beat it up. It's clear coat. The clear coat on your car is UV resistant and it still flakes off after some years. Okay. Health issues. There's just a lot of problems with UV radiation. Okay. Good thing for us, amazing thing for us. The ozone layer absorbs that. The problem is if the ozone layer is thin or damaged or like has the hole, you probably some of you heard of the hole in the ozone layer, it it doesn't really absorb this stuff. It lets a lot more UV through. It causes issues and stuff. Okay, so back in the 70s, they determined, hey, there's damage to the ozone layer, and we believe it's caused by improper use and handling of CFCs, chlorinated fluorocarbons. CFCs are composed of chlorine, fluorine, and carbon. That's why they're CFCs. Interesting. And they're also HCFCs that include hydrogen, hydrochlorofluorocarbons. Interesting. So what they found out was if you're not handling this right, if you're ventilating these CFCs and HCFCs, they're actually contributing to the depletion of the ozone layer. Okay, if you follow me so far? Remember the ozone layer is like this, it's like a shield, but it's not a force field. It's just a thick layer of O3 that'll absorb the radiation. Cool. Makes sense. It's not like we lost our force field here. It's not like the Iron Dome is down, right? It's just different. All right. Now, one of the major sources of the CFCs was the refrigerant R12 used in mobile HVAC. Right. And that changed everything right there. They're like, hey, we think that CFCs are being vented in the atmosphere and they're like messing up the ozone layer. Okay. And it might be your hairspray. Psh, but, this part is way outside of what I really know. They're saying that it was a major source was CFCs in mobile HVAC. So that's R12. They're saying R12 was causing a lot of this. So if we go back, right, we're at 1234yf. We were at R134a. Some of your hoopty cars are going to be R134a. It's a great refrigerant. It's way cheaper. If we do demos, we'll probably do R134a because it's cheap. R1234yf, pretty expensive. All right. So R134a was great. I thought it was great. However, R134a was so expensive compared to R12, people were shocked. Like back in the day, I wasn't really there for this, but when I first started, this would be my first year in the dealer was 2003. The R12 was still around. If a car came in, we weren't really charging it with R12. We were updating it to R134a, but I'd hear the stories. Like they would say R134a, it's so good for the environment. It's so healthy. It's so awesome. But it's so expensive. Now I'm telling you, R134a seems cheap compared to R1234yf. If you roll in and you want to buy a 12-ounce can of R134a, I actually took a picture, I have it on my phone, but I'm pretty sure I can remember the price. Okay, so right where we were at, I was trying to say the price on refrigerant, which I did get pulled up, and now you should be able to see. You can that fuzzy zoom screen, which I can't clear. I'll show you what I see. $12.99 for R134a. Will anyone take a guess what it is for R1234yf? Anybody?
$60.
You're not super far off. Ooh, it's hard to see. $79.99. All right. So back in the day, we were like, oh, R134 is expensive because R12 was like 1/10 of the price. And then it was like, oh, R134A feels cheap when it's $13 compared to $80. So the R1234YF is much more expensive. So a lot of technicians are going to be kind of bitter and sour and be like, oh, because R1234 was cheaper. Some of the really old school techs are going to be like, what the heck? Like, we were told R134A, you could basically use it as a soap. Like, it was amazing. It was great for the environment. It was practically like a fertilizer. It was so good. They were sold on how much better R134A was, but now they're saying it's bad and that we need to get to R1234YF, right? So I just want you to know the historical context so you can understand sometimes why techs are going to say some dumb stuff. Sometimes it might be true, and sometimes it's not totally true. So my job is to give you the facts. I can give you the facts. Here's the problem with R12. Ready? This screen will actually summarize it all. So if you look at this, I'll tell you the exact problem. Well, actually, just for fun, does anybody think they know what I'm about to say? This will tell you exactly what the issue is. Here's a molecule. You guys can see, let me minimize this so I can see a bit better. If you look at this, this is your molecule. That's a CFC, R12. So here's R12 right here. R12 just chilling right there as a molecule. When the sun shines on it and gives off UV radiation, this is what happens. You see there's chlorine, chlorine, chlorine. And then there's fluorine. And I forgot what the other one was. The other one was chlorine, and carbon. Of course, carbon. Right there. The UV radiation hits it. Look what happens. Can you guys tell that's a chlorine atom? A chlorine molecule will separate. A chlorine atom will separate from the molecule of R12. Then this chlorine molecule's like, yeah, la da da, let me go over here. And then it's like, oh, hey, look at that. There's 3 O's. O. What is 3 O's? Do you remember?
Oh, it's the ozone.
That was the ozone. So the chlorine molecule goes and rubs up against the ozone molecule, and the ozone's like, you know what? I'm going to break off one oxygen and have that oxygen pair up with a chlorine atom. And that leaves 2 O's. Is 2 O's ozone anymore?
No.
Here's your 2 O's. So it was ozone. By the time the chlorine molecule takes one of the ozones, it becomes O2. That's just oxygen. And then that chlorine and that third oxygen that it pulled off becomes chlorine monoxide. So that chlorine monoxide is a result of the chlorine stealing one of the oxygens. Now, do you understand how your ozone layer starts to be depleted? You can't really argue with this aspect. Then from there, the chlorine moves on, it boots the old oxygen out, and it picks up another O. So that chlorine molecule will rip an O from ozone, ruin the ozone, and make it into oxygen only. And then fairly soon after, just ditch the old ozone, ditch the old oxygen, and pick up another oxygen. And it does it again and again and again. And it can do it for the entire cycle that it remains in the atmosphere. Does that make sense? So the cartoon of this would be, here's your R12, sun hits it, chlorine breaks off, goes over here and steals one of the oxygens, hangs out with it for a bit. It ruins the ozone, gets a new one, gets rid of it, gets a new one, ruins that ozone, gets rid of that one, gets another ozone, gets rid of that one. This thing just goes around. It's a home wrecker. That's what it is. It's a home wrecker. It's just tearing up the home there. The home was 3 oxygens, which was an ozone. Makes sense? And it does that literally over and over and over. That makes sense? That's how the science works. It's not really rocket science, but it's atmospheric science. Now, here's really the problem. That leads to a number of things. The reduction in ozone causes, the UV radiation and that type of thing. But there's another couple issues. So, like, some of these gases act as a thermal blanket. So, I actually edited this one, so it's not just a publisher slide. It's, global warming was a big term. And then at the end, you notice I changed it to, it's more recently called climate change. So some of these gases act like a thermal blanket, allows the sun's infrared heat to enter the atmosphere, but then traps it in. And so this climate change kind of looks like this. Here's your sun giving off UV, and that's solar radiation. Just so you guys understand, the sun doesn't heat the air, which heats the earth. The sun is sending energy in the form of ultraviolet rays, which don't heat the air in space. The air in space is cold, but it goes through the atmosphere and heats the earth. Cool. But then the thing is, like, some of that should leave. But when we have these certain gases, it's more of a blanket. Rather than leaving, it kind of traps it inward, right? So it's almost like, it's just kind of like wearing a sweater. These blankets these gases act like wearing a blanket or a sweater. And all of a sudden, next thing you know, you're warm. So we can warm it. Now, it's not warming at degrees and degrees. It's warming at like very small amounts, which, could probably contribute to some of the more severe weather and etc. This is the greenhouse effect. That's how a greenhouse works. If you're in a cold area, you have, a rounded shape, and a lot of times you put like a clear plastic over it, or if it's a nice one, like where Frosty the Snowman went to die, he had like a glass greenhouse, and inside the greenhouse, it was warm because the solar radiation would come through and warm the ground and warm the plants and warm the stuff, but that heat couldn't leave the glass. Make sense? That's the greenhouse effect. That's how greenhouses work. That's like a for sure thing. You can do it yourself if you want. Cool. So the reason that we look at that is because, again, these refrigerants are a contributing factor. So there's a couple things we have to know. All right. So if I jump to this page, I want you to be able to interpret this. All right. ODP, GWP, and atmospheric lifetime. Do you know what those means? Very good. Move on. No, I'm just kidding. I know you don't know. So here's the three things: ozone depletion potential, ODP, global warming potential, GWP, and the atmospheric lifetime is just measured in years. So an ODP, ozone depletion potential, is a rating of the amount of damage the ozone can cause, but we're comparing it to CFC 11. All right, so that was chlorofluorocarbon number 11. That's an old school refrigerant. So that's your base number. And if it's high, it means it's worse than CFC 11, right? Your ozone depletion potential, that's kind of like how the chlorine goes and breaks off one of the oxygens and it ruins the ozone and makes it just into O2 and chlorine monoxide, right? So that's the ozone depletion potential. The GWP is a little bit different. That's the global warming potential. So one of them is how the ozone's ruined. One of them is that greenhouse effect. Make sense? The GWP is calculated by measuring how much energy the volume of 1 ton of a specific gas as compared to the energy of 1 ton of CO2 over a period of 100 years. So for the GWP, we're using CO2, and we're stretching that out over the course of 100 years. So again, a high number would be bad. Make sense? And then the atmospheric lifetime is just the amount of time. So how long will the gas remain in the atmosphere doing these horrible things that it does until basically it stops damaging stuff. All right, so let's take a look. R12 has an ozone depletion potential of 1. It's just as bad. It's just as bad as CFC 11. Make sense? That's really bad. It's got a lot of ozone depletion potential. Kind of makes sense? Now, if it was R12 and we went to R134A, what would you say that improvement is? We went from 1 to not 0.5. 0.5 would be half. It's 0.05, right? It's like, that's a big reduction. You went from spending $1 to spending 5 cents. It's a 95% savings. Makes sense? So the ozone depletion potential of R134a was what I thought, the way that I came up, I thought was amazing. Makes sense? Let me put it this way. R12 was so cheap, people would literally, if they had a cold beverage, if they had a beverage like a soda, let's say a Pepsi, if they had a Pepsi on the toolbox and it was warm, they would literally go get the R12, hook it up to their gauges, open it up, and just literally spray R12 all over the outside of the Pepsi to make it cool. That's what they were doing. And that was probably horrible, actually. But it was inexpensive and they didn't care. And they got a cold beverage and had a nice cold beverage. And then R134a came out and they're like, hey, it's 10 times the price, but look at this improvement. We went from 1 to 0.05. That's nice. Okay. Now we'll jump into global warming potential. Yeah, it's got a global warming potential of 10,900 for R12. R134a dropped that to approximately 1,430. So it went from almost 11,000 to under 1,500. That's a really good improvement, don't you think? That's a great improvement. Yes, ignore R1234f. Ignore that for now. And the atmospheric lifetime of R12 is 100 years. It's 100 years. And that thing where it was home wrecking, ripping that ozone apart, it's 100 years of that. And then R134a was like, it only lives 14 to 15 years and then it's done. Can you see now, like, the perspective that I came up with? R12 to R134a, this is basically like organic. You could rub this all over your skin. It was so good. It was like nice. It was awesome. But then they realized, like, hey, we got some room for improvement. Okay, and one guy I respected really well, he said he felt like the requirement for R1234yf was like splitting hairs. So we went from 1 to 0.05 and we're like, yeah, we're chilling, but that wasn't good enough. So they came up with R1234yf. There's a whole history on that. We'll cover that. And that dropped the ozone depletion potential from 0.05 to 0. He called it splitting hairs, and I can kind of see where he's coming from, And in ozone depletion, that's a great improvement, but like we were already pretty low. You were paying $1, and then we got it down to 5 cents. Now it's 0 cents. Like that was the bigger change was R12 to R134a. Cool. Now, here's where I don't totally agree with the splitting hairs, but we had a global warming potential of, remember, 10,900. We got it down to 1,430. Yeah. R1234f is 4. So that's a pretty big improvement. I think that's a pretty big improvement. Gotta admit. I don't know if it's worth 10 times the price, but it's a pretty big improvement. And it doesn't matter if I think it's worth 10 times the price. It's into legislation. You can't get R134a. They can't make R134a. They can't sell a vehicle that comes with R134a from factory. It's done. Now let's look at the atmospheric lifetime. 100 years for the R12. We got it down to 14 to 15 years. That was great. But look, 11 to 12 days for R1234yf. Now that's like real organic. That's like non-GMO. Like that's like guilt-free, free range. That's going to be really good. So now you understand the details as to why. R12 was a no, R134a was the savior, and then they're like, you know what, after 20, 30 years, it's not that great, let's go to R1234yf. The R1234yf was $90 when the R134a was 13. Just, it's more expensive, okay? So now, here's how we got to that point. Now you know the facts, though, right? Those are facts. Hard to argue with those. Now you can kind of see some of the things that have happened. So in 86, scientific community had proven that CFCs were causing the damage to the ozone. We had the first global meeting of the world's nations occurred in 85, and they created something called the Vienna Convention for the Protection of the Ozone Layer, and 20 of the world's largest CFC producing nations agreed we need to regulate the use of ozone depleting chemicals. One of the main things was like R12 type of thing. A lot of the refrigerants, 2211, a lot of those. Okay, so they agreed. 20 of the world's largest companies. Now, if it was a third world company, they're like, we don't care. We will light stuff on fire and burn it for whatever we need to burn. They don't care. They'll deforestation. They'll do all that type of stuff. So this isn't to say all the countries agree to this. This is to say 20 of the world's largest CFC producing nations. You can't be in the third world and producing R12. Okay, like you do that in a lab. So if it's some a country where they still don't wear pants and stuff, they weren't at the meeting. They don't get it. They don't know. They're burning the Amazon to make room for, I don't really know. Whatever. Okay. So but 20 pretty civilized high production countries agreed on this. And then here's the whole timeline. It was kind of interesting. So in 87, the Montreal Protocol was signed by all the governments. And when we say all, we mean the 20. It's not going to be, like a small country in Africa. They weren't there. They weren't at the meeting. They didn't sign. They don't care. Okay, then in 90, the Clean Air Act was signed into law in the US. And then shortly after that, in 92, the US government came up with this thing called the 609 requirement. So technicians that are going to handle refrigerant after 92, January of 92, they had to have the 609 certification, which means guess what? Y'all got to have the 609 certification. So we're going to be working on that end of the week. All right. So you're going to get the 609. It's an easy test. It's not something that's really difficult. It's you can study. There's a whole study guide. It's basically open book. You don't have to go to the ASE test center. You can do it through two ways. I'll show you at the end. Okay. Anybody to legally handle refrigerant has to have that 609 license. Mine's on display in the office right over there because when we buy refrigerant, they need to see someone's license. Right. And then in 92, recovery equipment was required for all refrigerant repairs. Venting refrigerant to the atmosphere became illegal. So you know, before July of 92, it was okay to just pull a line off and let that R12 out into the atmosphere. Just vent it off. It would go up in the atmosphere. Now you understand why that was kind of an issue. That R12 would go up there and be the home wrecker right there. Right. So they said, hey, you can't do that anymore. Now it's illegal. Okay. Makes sense. Then the European Union were like, hey, you know what? In 2006, we're going to phase out R134A. They don't know what to use. And this is kind of how politics work. And I'll be really honest with you. It irritates me when one person is able to file a complaint without having to have any ownership of the solution. All right. I find almost every time that's a toxic relationship there. If somebody just says, well, that's not good enough, and that's all they have to do is just like your job is just file complaints. Your job is to identify it's not good enough. And yet you pass it off onto other people to solve it. Okay. So now I'm showing you a little bit more of who I really am. European Union, a bunch of politicians get together and they're like, hey, R134A is no good. And they're kind of like, all right, but what do you want us to use? And they're like, well, we don't figure problems out. We just have meetings in the Senate and we point out that there's a problem. We don't know what you're going to use. We don't know. We're not engineers, but we know you can't use that though. So you better figure something out. And they demanded that I have a GWP of below 150, right? So that was 2006. And then guess what happened in 2011, right here, European Union delayed the phase out of R134A. You know why? Because they couldn't find a good replacement for it. They were like, hey, yeah, you signed this into law that we need to get rid of it, but like, we don't have anything. We got nothing. We don't have a fix. So why don't you go ahead and you tell the people driving their cars they can't have AC anymore, and then they'll vote you out of office and you go back to where you should be. In the basement, mom's basement, I think where the politicians would go if you asked me. I'd send them right there right now. But then the problem was, yeah, the US EPA, we started making some progress and stuff. And then the US EPA approved R1234yf for use in new mobile HVAC systems in 2011. So shortly after, we were like, hey, we got something. We found something that'll work. But then like a year later, Daimler, which was Daimler Chrysler. Oh, actually I skipped. Yeah, I think I got it. Did I skip something? Yeah, in September 2012, Daimler Chrysler said, hey, we're not going to use 1234yf. And the reason why they're going to use R134A still is because it was unsafe. What do you think they mean by unsafe? Anybody know? I'll give you a clue. Thermal event. Heard of that? The R1234F, if you get in the right type of accident, it catches fire. It's flammable. I think R134A could burn under very specific circumstances, but R1234YF was much more flammable. It was much more dangerous. So like, hey, we're not going to put this in cars. I actually tend to sort of, that makes some sense to me. Say like, hey, you politicians are like, hey, you need to use this different thing, but like, if our cars get in accidents, they crash cars. If they start burning, we're going to get sued. We're not going to use this. So they blew the flag, they blew the whistle. They're like, no, we're not going to use it. And then European Union decided shortly after that in 2017, they're no longer allowing R134A. They're done. And then just after that, Daimler was like, oh, you know what? We will use R1234YF. Fine, we'll use it. They kind of caved. But they wanted to see newly developed safety measures, make it a little safer. Cool. And then in 2020, which ended up really being like production year 2021, R134A is no longer used in the US as a new car, right? So you can buy R134A, no problem. But any new car made after that point, so it's a 2021 model year, they don't come with R134A. They have to come with R1234YF. Cool. And then in 2026, it's totally no more new cars, no more nothing. I think they actually already phased it in anyway. I don't see any new cars coming with R134A. Cool. So that's the timeline. Now you can see why we went from R12 to 134A and then R134A to R1234YF. It was really through government regulation. The manufacturers were happy with R12. They were like, R12's sweet, it cools good, it's cheap. Technicians were like, yeah, this is great. It's easy for us to sell repairs. It was cheap enough where people wouldn't fix them, though. That was kind of the negative. They'd just be like, whatever, just blast another $1 worth of R12 in the car tomorrow and we'll run it for another week. It's a small leak, no big deal. We'll just blast R12 in there before we go on vacation. And then R134A was like, hey, yeah, we should fix the leak. And now it's like, honestly, it's probably going to be cheaper to fix the leak on a R1234YF than charge it alone. So the price has drastically changed. Again, the driving force, government regulation, meetings, conventions, countries getting together and saying, yeah, we're going to do better. But I have a little chip on my shoulder with them because the people in that room were saying like, we want. But then when it comes to development, it's like, where are you at? You're running for your next political office position. You know what I mean? And so again, Montreal Protocol, that's when they really got together and like, hey, we need to address this ozone thing. This is the 609. We talked about the timeline. So this one, again, we're going to cover how you get the 609. You will all have your license before next week. You all be licensed to handle refrigerant. Or if you don't, you won't be able to handle refrigerant. Good luck passing the class. That's mostly going to be handling refrigerant. Okay, so you're all going to be good. It's cheap. It's like $15. Cheap. And then again, remember, all the reclaimed refrigerant has to be recycled. You can't just vent it to air, etc. We also have to keep records, approved equipment. Some of you guys, when you get hired, your dealerships will have you do like an onboarding package, and you might have actually got the 609 because they have to keep record of how you're certified. Okay, so that some of you might bring a 609. You don't have to pay for the 609, but if you don't have it, you're going to have to prove it. You might as well do it through ASE. Cool. So there's some other details. They have a lot of sections of the Clean Air Act stating what we do and why we do it. So the reason we do the things we do is because it's law. Makes sense. It's like federal initiative. Cool. So 612 required unique service fittings. So for example, if you try to hook up your R134A machine to a R1234yf, it's just not going to work. That's what I was saying. You don't really have to study that sticker because the fittings are unique to YF. The fittings are unique to R134A. The fittings are unique to R12. Kind of makes sense. So it's not that crazy, but they do have labels. One of the things with the newer systems, they have to have a high pressure cutoff switch. So if the pressure gets too high, it has to shut the compressor off so it doesn't overpump and potentially blow it up and potentially cause a flame, fire, etc. Thermal event. Okay, makes sense. And then if you use anything with R22, you need to have barrier hoses. So back in the day with R12, the hoses were basically they were a little more porous. A barrier hose is a very, very tight molecule hose, and R12 was kind of a larger molecule. It wouldn't really get out of those, but R22, R134A, 1234yf, they're all smaller. Those will actually have a tendency to leak more. So if you were to just use the old school R12 hose, but put the retrofit to R134A, the R134A is going to have more of a tendency to leak. That's why to do a proper retrofit, we should really change the hoses to barrier hoses. You should have it reworked. However, you could do a retrofit and just run the hoses. Just know it's going to lose refrigerant over time. How fast? Tough to say. If it lasts a couple years, you could at least get a couple years and then have to recharge it every couple years. Cool. All right, and then remember that European Union was pulling pretty hard on this too. European Union was going for it a little bit ahead of us. And then again, the 609. So to be licensed, you need the 609. This is how you're going to get it. I'm going to hold your hand on exactly how to go to the website. You could also get it through Max. If you got it through Max at work, that's fine. But if you didn't, we're going to get you with the ASE. Okay, that's I believe end of the week. I believe this is Thursday, but let me double check the schedule. It's coming up quick though. Cool. Now, here's a little bit about how we store and handle. Okay, the EPA's got all these guidelines on how we need to store and handle. It's actually a federal law to, let's say that you have a used container and it has refrigerant in there. It's actually a federal law to reuse it if it's disposable. It's also federal law that you can't like just throw it in the trash. Okay. So here are the containers, and these are disposable. See this word disposable? These are disposable. It's one-time use. R12 is kind of just like a tan white color. R134A was blue. I like that. Then R1234yf came back to like white tan, but it has a red band. So if you see the red band, you know that's the more expensive YF. You can actually see this refrigerant produced by Honeywell. So there's some pretty big companies. DuPont was really big. You know, there's some of these companies who produce this type of stuff. There's not a lot of companies that do produce it, but they're big names usually. Cool. So let's say like this is a well, 1 pound is probably 16 ounce, but this is like what I was showing in that picture. Something like that would be under 20 bucks. $13 was the price I saw, but that was for 12. So that's a little small, but you can buy them like this for your own personal use. Generally the shop's going to buy them like this. We get a better price. That goes right into the machine. We charge the machine with that. Then it charges from the machine. But one fun thing I like to point out with this is R134A made by DuPont. They actually call it Suva. Who has heard of Freon? Anybody?
I have.
Technically, R12 is Freon. R12 was like the trade name. Freon. Freon was R12. R12 was Freon. Freon means R12. R134A was called Suva, but nobody really liked Suva, so we just call it R134A, 134A, 134, 134, right? But then it's kind of like ain't. Have you guys ever heard ain't a word? Ain't's not in the dictionary. It is now. All right. Ain't was not a word, but then so many people kept using it, they made it a word. R12 was Freon. R134A was Suva. Everybody called it Freon. Now they make R134A that says Freon. So now Freon doesn't even really mean anything. Freon used to be specific. Now Freon is like everybody says Freon. Nobody says Suva. I've never heard anybody say Suva. Okay, but here you're seeing R134A in the disposable personal can, a 1 pound can, Suva. When we're dealing with these tanks and stuff, remember these tanks actually get tested and they have a date stamp. So if you're using a used tank, you should actually test this. You should actually look at the date the last time it was tested and they'll tell you when it expires. So we don't usually do it like this, but you can. This one's painted yellow, so this is a hazmat. This is a trash one. If you were to connect to a car and it were to have R22, you'd recover that into this yellow one. Or if it's a mix of things and there's some real crazy people who put propane in there and it does work, you could consider this hazmat. It needs to be clearly marked, but this isn't an approved one. It's kind of like a propane tank. It has to be tested for rust and ability to hold pressure and stuff. Cool. So that's a good one. Now let's talk about the different types of refrigerants and the oils, which is also kind of fun. So again, when we look at refrigerant as a whole, the refrigerant itself is responsible for absorbing heat and releasing heat, right? So if it's AC, we're going to absorb heat in the cabin. We're going to release it under the hood in the condenser. If it's a hybrid or EV with a heat pump system, we're going to use the AC to make heat. We're going to absorb heat from the condenser. We're going to let it out in the cabin inside the car. That's how we make heat, right? So when we talk about refrigerant, we're mostly really talking about AC, but on a hybrid and EV, a lot of times we're using the AC to make heat, kind of almost like running it in reverse in a sense. That'd be the most simple way. The evaporator does what the condenser used to do, and the condenser does the evaporator used to do. We get some valving and it changes the flow. Okay. But what's true about the refrigerants, they're all responsible for that. Carrying the heat, moving the heat, basically. They're always a stable chemical formula used to transfer heat, mostly while changing from a gas to a liquid, back and forth, back and forth. We need to be able to change it from a gas to a liquid and from a liquid to a gas. So to be able to do that, we need stuff that has a very, very low boiling point. So anything that has a very low boiling point could make a good refrigerant because we can have it change back and forth, liquid gas, liquid gas, liquid gas. As we get more into the science, that'll make more sense. But for right now, that's only the requirement. Those are some of the only requirements of refrigerant. So like here was R12, that was Freon, chlorine, chlorine, hydrogen, carbon, fluorine, right there. That's the molecule R12. Dichlorofluoromethylene. Okay, but it's in the family of CFCs. Cool. It was the first common refrigerant in vehicles, non-flammable, non-toxic, stable at all temperatures, doesn't react with aluminum, steel, or copper, soluble in mineral oils. It's got a boiling point of, get this, negative 21 degrees. If it's negative 21 or warmer, so like if it's negative 20, if you dump that refrigerant out, it boils. Makes sense? It's crazy. If it was negative 30, you could dump it off and you could actually potentially see it in liquid form. That'd be interesting. So it's found to be one of the leading causes of that ozone layer problem, remember? And it was banned by the governments in 94. So after 94, you can't get it. So that refrigerant was a good one, but it wasn't one that we could carry on into the future due to the environmental concerns. So then we get into tetrafluoroethylene, R134A. Again, this is like the joke back in the day. This was like the cleanest organic. Stuff was nice. This was great. Now you can see it's got a bit of a different design. You can see quite a few fluorines, a carbon, and a the heck is the H? I actually don't remember what the H is. But either way, it's not real important. It's just a different chemical makeup, right? Some of the similar atoms, but we're adding the H. Just can't remember what helium, maybe, whatever. Similar though, boiling point's -15, so that's fairly similar. It was the only approved substitute for R12 that can be retrofitted. So if you got an R12 system and you can't get R12, which by the way you can, but the price of R12 is way up now. They haven't been making R12 in like 30 years. So if you got R12, somebody's been keeping that for like 30 years. It's expensive. So if you want R12, you could potentially get it, but it's going to be hard to get. So normally we're going to retrofit it. You want to get rid of the R12 and go to the R134A, that's great. But R134A is the only refrigerant that was approved to go in an R12 design system. Cool. And then again, the R134A was a lot better for the ozone layer, but it wasn't great for the greenhouse gases. So that global warming recoined is climate change. Probably R134A has been contributing to that. Okay. And look, it works with a different type of oil, PAG oil. So hold up. This one works with mineral oils, R12's mineral oils. R134A was PAG oil. But look, this is the thing. If you mix PAG oil with mineral oil, it creates a hazardous gas. It can corrode the AC system. So this is the thing. If you're going to retrofit it from from R12 to R134A, we do not recommend that you use PAG oil. There's another type of oil that doesn't make a hazardous gas with mineral oil. So if you want to do a retrofit, you buy a retrofit kit. It comes with a specific type of oil. I can't seem to quite remember what the name is, but we actually cover retrofitting later. So this is just an overview. Right. But what they did to make sure you don't accidentally, unknowingly put PAG oil in there is we changed the fittings. So if you want to do a retrofit, you got to get rid of the R12 fittings. You got to get rid of the R12 refrigerant appropriately, not vented to atmosphere. And then you got to put the R134A fittings in, charge it with R134A, and oil it with an oil that's compatible for both. PVE oil. I'm gonna think about that just a little bit more. I'm gonna probably randomly think of it, but I can't remember. And then again, if you have R12 equipment, it can't be connected to R134A system. They change the fittings, so you can't be contaminating each. Cool. So there's your R12, and there's your R134A. R12 is old school, threaded on. R134A is like more of a quick connector. They do have threads inside, but it's more for the valve, for the Schrader valve. All right, and then we got into the YF, right? So the tetrafluoropropene. You can see more complex molecule a little bit. It's not even in a CFC family. It's a HFO family. So that's why sometimes they'll say like HFO R1234, HFO 1234YF. You know, it's in a totally different family. So what's interesting is DuPont would call it Opteon, Honeywell would call it Solstice, but honestly, nobody calls it either of those. So it'd be kind of fun for you to go around the shop and be like, hey, does that car take Suva or Opteon? And they'll be like, are you talking about Transformers or something? Like, if nobody uses these names, we just call it R1234YF. But technically, those are trade names. Kind of fun. Cool. And then again, like we discussed, it's there for government regulation, not only US, but other governments too. Environmental damage, it's the latest and greatest, better global warming potential, better atmospheric lifetime. The boiling point's good. That's a slight concern, slightly flammable. But one of the arguments was you're driving around with 15 gallons of gas in the car. Like, Chrysler, why are you complaining so much about your slightly flammable refrigerant when you're carrying gas? So I kind of see what they're saying. I mean, to me though, at least the gas is liquid, and I don't know, but cars are dangerous. It is what it is. So we're kind of cool with it now. Now we'll use them. typically your gas tank's not in the front end though. That's kind of where a lot of your accidents happen. They usually protect it a little better. Your condenser's just hanging out right there, getting ready to have a hole punched in it. So I don't know. Here's what it is. And then you notice it uses a PAG oil, but it's a slightly different PAG oil. And then, so if you have R134A PAG oil, that's good for R134A. But if you have R1234yf, it should be an R1234yf PAG oil, not the same, just a little different. Okay, but then let's say it's a hybrid or EV and it's got an electrically driven compressor. Again, that's probably going to use this polyester oil, POE oil. And then sometimes some cars will actually use the POE in a belt driven compressor. It'd be on the sticker. It'd mostly be in hybrid, but if it's on the sticker and it says POE, you need to use POE oil. Right. And so then again, the YF ports are different. So if you have an R1234yf car, you can't connect your R134A machine to it. It just, the ports are different. It doesn't work. Here's the three of them. You saw this, this is new. Totally different fitting design. If you want to put gauges on an R1234yf car, you need R1234yf gauges. So now if you want to be able to work on R134A and R1234yf, you need two different sets of gauges. It's kind of a pain. David, you can go ahead and ask your question. Go ahead. I saw that pop up.
This is all to like prevent cross contamination and ruining systems and whatnot.
Exactly. We can't have this refrigerant mixed with that refrigerant, this oil mixed with that oil. They're not compatible. The main concern is the R12 oil with the R134A oil. That creates the hazardous gas. It'll corrode and cause damage. So it's all exactly what you said to prevent cross contamination. It's kind of similar to like the gas and the diesel nozzles. You ever notice they're actually different size, different colors? Like you're not supposed to be putting diesel in the gas car, even though sometimes it happens. If you had to actually connect it with a fitting, nobody would be able to accidentally put diesel in their gas car. But technically, there's somebody will find a way. They'll fit it. So we make these unique for that exact reason. Cool. So when we look forward, and I don't know a ton about this, but I've been hearing more about it. They were even talking about using carbon dioxide to be the replacement for 134A or even the replacement for 1234yf because it's got even better global warming potential, even lower ozone depletion, even lower atmospheric lifetime. This is very low carbon. See, it's what you breathe out. This would be amazing, but there's one problem. Like you can even see global warming potential is just one that's so low, but this is the problem. To run carbon dioxide, we'd have to have much higher pressures, like 10 times higher. So it'd be a total different system, different types of lines. I don't really know how they do it. Big compressor. It's going to add a lot of cost. It's going to be much harder to run, probably draw much more energy from the vehicle because we got to run, not 200 PSI. You got to run like 2000 PSI. Okay. But just so you know, just to consider it, carbon dioxide could actually be a refrigerant if we ran high enough pressures. Make sense? So continuing with that, sealant. Sealant from our perspective in this class is bad. This is like if you have a tire that's leaking, you put a bunch of Fix-A-Flat in there, like that's not good. If you're in a jam, okay. If you roll to the store, a lot of these refrigerants that you buy off the shelf with the fancy little hose and the little trigger, those will come with a sealant because they know if you're in there buying it at O'Reilly's, you're probably got a leak and you're not going to fix the leak. You're just going to blast the stuff in there. So the typical off the shelf trash is going to have sealant. We don't want sealant. We don't deal with sealant. Sealant's not good. Diagnose the leak, fix the part. Sealant's not the way. Makes sense? But it is a thing. The problem with sealant is if you go to recover the system and the sealant goes into your machine, it's contaminated. So what we're not supposed to do is just be hooking up our machine to any old car that comes in. Make sense? You shouldn't be hooking it up and hooking it up and hooking it up. Well, unless you want to get it contaminated. Okay, now you could take this in several different ways, but I'm just going to keep it. You shouldn't be hooking up your machine to cars that might have sealant in them, because now your machine has sealant in it, and every next car that you work on, now all those other cars have sealant in them. Make sense? So before we hook our machine up, we actually should do a sealant test. Make sense? One of the ways that the sealant works is it goes to the hole and it reacts with the oxygen, and it's going to make like a little kind of like a scab, like kind of like Fix-A-Flat. It's just nasty. It's not, it can clog up orifices, thermal expansion valves. It's just not good. Cool. So we should do a sealant detection. Now, this is something that you typically in the dealer, we're not seeing cars that are having sealant, but in the independents and in the aftermarket, they're going to have cars that have some sealants. If you hook up an identifier that's going to identify the type of refrigerant, which we'll cover in a second, the sealant especially is known to damage the identifier. And the identifier is a tester to tell if that vehicle's refrigerant's contaminated. It's kind of like if you were thinking about hooking up your machine to a car, you'd be like, hey, let me get a test. Let me see if everything is, if there's a contamination or not. You'd be like, get the identifier out, hook it up to that thing. Oh, beep, 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 100% pure R134A. Beep, 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 90% R134A, 5% R12, 5% propane. My machine's not getting connected to those fittings. Does that kind of make sense? Okay, I think you got what I'm saying. So with that, here's what the detector looks like. Here's how you actually do it. You'd actually go to the fitting, get the adapter. You'd actually literally fill this syringe with tap water. Literally going to put water from the syringe on the test cartridge, hook up that cartridge, you can see, with a hose right there. And then you're going to hang it. And then what's kind of crazy, when you hook this up, you should actually be able to see flow, and your flow meter is going to like kind of move a little bit and then stabilize. So like right there, if you were to leave it right there, that means that it's flowing. And if it's flowing, that's a good sign, right? And if it keeps flowing for 2 to 3 minutes, it's probably because there's no sealer. But if it starts off flowing kind of strong and then the flow stops, it's because the sealer sealed it up. Makes sense? So, or if it even decreases, like right now we're at a 2. If it drops to a 1 after time, that'd probably be like, hey, sealer is sealing up this leak that we made on purpose with this hose. Okay, so that's the overall. Again, it's not something that we really super commonly do, but that's a way that we could test for sealant. The identifier doesn't test for sealant. This is the identifier. It's the way that we can tell what type of refrigerant's in the system. Connects to low side fittings. It runs a little test, does a little burp, does a little beep, and then it tells you what the percentages of each are in there. Okay, that's what it does. So like right here, we're just going to go through the steps. We hook it up. It's going to warm up. It's going to make some sounds, some noises. Sometimes you got to wait a while. Ready to test. Go ahead, connect it. And then it's going to run the test. It's real easy, a couple buttons. And then if you look right here, R12, 0%, R22, 0%, hydrocarbon, 0%. That's pure. We're good. Hook up our machine, our gauges, whatever. That one's good to go. Cool. But if it has hydrocarbon contamination, that's generally like propane. Makes sense? So that's what we'll do. And it'll tell us what type it is that's in the system. And then again, we could do this. That's going to tell you if it's contaminated. This next step is actually determining what the refrigerant type is. This is something we wouldn't do real commonly. Where we're working on cars that are pretty reasonable. If someone is working on a car that just came from TJ, I'd probably take a second look at that car from TJ, because you have no idea what happened there. You don't have any idea. What happens in TJ stays in TJ, right? So if that car went down to TJ and the AC wasn't working, they very well might have put propane in there. They might not have had no R1234yf, but they got propane. Makes sense? So if you want to know what type of refrigerant is in there, there's actually a really interesting way. You can hook up your gauges, look at your gauges, actually measure the temperature. So these gauges measure pressure. Right here, I'm seeing 100 on the high. We would really normally do this at static, so it wouldn't be running. So let's ignore the low. Let's just look at 100 on the high. You could look at 100 psi and then measure the ambient temperature, what the air temperature is outside, and you could look on a chart called the pressure temperature chart. The pressure temperature chart is going to be specific. So if it's R12, there's at, let's say, 100 psi, it would be right around like 90 degrees out. If it was R134A and 100 psi, it should be 100 degrees out. If it's R1234yf and it's 100 psi, it should be 110 out. So if, let's just say it's 90 out and it's 100 psi, you know that's R12. If it's 100 out and it's 100 psi, that's R134A, right? So I made those numbers up. Those are roughly correct, actually, but you'd want to look at the chart and be like, what's the temperature? What's the pressure? And whichever one matches the chart, you have one chart for R12, one for R134A, one for R1234F. One of those will match. That's another kind of a cool way to tell what type of refrigerant it is. See, here's checking the ambient temperature. That one was 80. So if it's 80 outside and you got 100, that sounds more like R12. Okay, so that type of thing. But again, the identifier is going to do a really good job at that. So you know. And a lot of the new R1234yf machines, they have an identifier built in because that refrigerant's expensive and it's a little hazardous. So they're going to have that identifier. The first thing it's going to do is check it as soon as you hook it up. You can't even override that. It's just going to do it. Okay, so let's just say that it was contaminated. What do we do? Well, you don't hook up your machine to it. You get this recovery only machine and you can recover it into this container that's painted. Remember that yellow painted one? And that becomes like hazmat. Makes sense? So your contamination, your TJ propane, your old school R12 or whatever, that goes in a contaminated tank and it's labeled, and someday we'll get rid of it, but not right now. We're going to keep it for a long time, probably. Cool. And so again, it's got to be rated correctly. It's not a disposable. This is a legitimate one with a stamp and it's good and the date's good and it should be stored above level ground, out of the sun, etc. Should never go above 80%. Should be inspected monthly, etc. All right, so different types of oils, and this is, remember, this is just an overview, give you some context. So depending on the system, they're gonna use different oils. For example, the 4 types being mineral oil, R12, PAG oil, R134A, POE, typically hybrid EV, and polyvinyl ester. There you go. That's for the retrofit. That's an oil that works well with mineral oil and PAG oil. Or that's an oil that if it had mineral oil, you would not want to put PAG oil in. You'd want to use PVE oil, polyvinyl ester, because if you didn't and you put PAG oil in, that can make that hazardous, right? On the retrofit. Okay, PVE. Each oil can have different viscosity. So you can have low, medium, or high viscosity PAG oils. Depends on what the car calls for. How would you know what to use? The sticker, remember? Remember the sticker? The sticker will tell you. Refer to the underhood sticker. Cool, that's why I pulled that in there. Here's a mineral oil, for example, clear to yellow, typically R12 systems. PAG, that's going to be the common one. That tends to be like light blue. If it's contaminated, it can turn brown or black. It could be PAG 46, PAG 100, PAG 150. So 46 is watery. 150 is honey oil. It's thicker, right? It's just viscosities. And again, here's what they would look like: 46, 100, and 150. You can see those are pretty clear. Anyone ever seen these and they're green? That's what color you're going to see all of our oil. The reason why is because I personally add dye to all the oils. If we service a vehicle, I want dye in there. A lot of times we're servicing a vehicle because it has a leak. If you don't put the dye in there, you can't see the leak with a UV light, with a black light. You're relying on the sniffer and stuff like that. I personally just put the dye in the oil, and then every time I oil it, it gets dye. That's how I do it. You could do it how you want to do it. Okay. Cool. And then if it's R1234yf, hey, here's another PAG oil, but it has an additive package, acid reducers installed. So that R1234yf tends to get a little acidic. So we need to run the acid reducer package in the YF. Okay. FYI, PAG oil can irritate your skin, cause paint damage, and remember, it's hygroscopic. It's going to absorb oil. I mean, it's going to absorb moisture, which is going to require it to be replaced. So it needs to be sealed. But if a car, for example, is in a collision and the condenser's out of it and the lines are just hanging there for a month and it's been warm and cold and rainy and sunny and it's been exposed to a lot of moisture, that PAG oil is going to be absorbing the humidity because the system is not sealed because the lines are disconnected because it was in a crash. That could be a little bit problematic. That oil is going to absorb too much moisture. It's going to have some issues, and it can change it into other compounds, hydrochloric acid, and start damaging the system. It's a mess. Cool. And then here's polyester oil, and they do have polyester is a little bit newer style, and then they have that polyvinyl. They have other stuff too, but if a vehicle calls for this is more of a synthetic. If it calls for it, that's what we need to run. For example, Honda does in this case. Okay, and then there's your polyester aftermarket, and so then again, this is chosen for R12 to 134A because it doesn't cause any damages. And it can also be used for high voltage compressors. And here's your polyvinyl ester oil. And then again, compatible with R134A, R1234yf. This is compatible with potentially both. And we're seeing this on some of the Korean vehicles more so. And it's a good one for electrical insulating. So again, if it's hybrid electric and we're running high voltage compressors, electric driven, this is going to be a good one. And it's, both of these later ones are pretty good and good potentially for the hybrid EV type of stuff. Okay. So there's your whole big old overview of the context of how we're going to do this AC type of work. So now you know about the environmental, you know a little bit about our old systems, you know a little bit about the safety, a little bit about the refrigerants, a little bit about the oils. We haven't even gotten to any technical stuff, but we'll get into technical stuff next time. Okay, so you guys did it. Congratulations. That was your first live one.